Good morning. Today we are going to handle another subject referred to as electrical circuit analysis. Electrical circuit analysis. It is more referred to as ECA. And this is a subject that will give us foundation in machines. So anytime, and it's done in module 2, anytime you're studying electrical circuit analysis, the foundation of this subject is the one that gives us the core of actually being the specialist in electrical machines. Another thing is that it also helps us understand how the circuits operate. So basically, it's a wide subject as it goes around 14 topics, which I'm going to list down here, so that you're able to follow on each topic as it comes. So the topics we expect to cover here are: number 1 is network theorems. In these network theorems, we have a term referred to as Thevenin'S theorem. We have a term referred to as Norton's theorem. We have a term referred to as Millman's theorem. We have whatever also referred to as maximum power transfer theorem. So these are the theorems we shall be able to handle. Topic number 2 is DC transients. In DC transients, we have the LR circuits. We have the CR circuits. We have the RLC circuits. The topic number 3 we shall have here is complex waveforms. And this was whatever I have here is in complex waveform we have the types of waves, types of complex waves. We have power in a complex waveform, power in a complex waveform. Then we shall talk also effects of capacitance, resistance, and inductance in a complex waveform. Then we shall have topic number 4 is two-port networks. Two-port networks. Here we shall talk about A, B, C, D constants. And these are constants in transmission line. We can have topic number 5. Topic number 5, we shall have three-phase systems. In this we talk of star networks. We shall talk of also of delta. And also power in three-phase systems. The topic number 6. Topic number 6, we shall have three-phase induction motors. Here we shall talk about the construction. We shall talk about the revolving flux. We shall talk about power in three-phase motors, and we shall be having some calculation and derivations. Topic number 7, we shall have synchronous machines. So we talk about the methods of starting synchronous machines. We shall talk about the construction. We shall talk about also comparison. With the induction motors. The topic number 8, we shall have what I refer to as special machines. In this special machine, we shall talk about the stepper motors, universal motors, stepper motors, universal motors. We shall also talk about single phase, machines. Then we shall talk about there are around 4 machines. We shall talk about what I refer to as reluctance, inductance motors, reluctance motors, and finally is the shaded pole motor. The topic number 9, we shall have what I refer to as filters. This is low pass filters. Then we shall talk about high pass filters. Then we shall talk about constant K filters. Constant K filters. The topic number 10, we shall talk about single phase AC induction motors. In this case, we shall talk about capacitor start, induction run. We shall talk about capacitor start. Then we shall talk about capacitor start, capacitor run. The topic number 11, we shall talk about C machines. So we shall talk about the construction, the starting methods, DC machine as motors, then DC machine as generators. That's all. So these are basically the areas we need to learn to measure on and to look upon in terms of application and in terms of different areas of developing the core mandate for studying, or for analyzing and getting out of to know about machines in depth. So we're going to start about the Thevenin'S theorem, which is going to be the first one. And whatever we need to understand here is the procedure and particularly the statement. So with procedure, it states that that the current which flows in any branch of a network, I said that the current which flows in any branch of a network, is the same, that which will flow is the same as that which will flow, which is the same as that which will flow in the branch. The branch, if it were connected across an electrical circuit, if it were connected across an electrical circuit, if it were connected across an electrical circuit, the EMF being equal to the potential difference which would appear, the EMF being equal to the potential difference, which would appear across the branch, would appear across the branch if it were open circuited. If it were open circuited. If it were open circuited. And the internal resistances and the resistance of the EMF source be replaced by their internal, resistances. The resistances, or other books refer to them as the impedances. So, and this statement, we need to know about the procedure. So, number one, we remove the load from the branch. Remove the load RL from the branch. Number two, determine the open loop voltage across the break. Determine the open loop voltage across the break, whatever we refer to as the Thevenin'S, that are referred to as the Thevenin'S voltage, VTH. Number three, remove all the EMF sources and replace them by the internal impedance. Remove all the EMF sources and replace them. By their internal impedances, and determine and place the internal impedances. If it was a voltage, if it is it is a voltage, replace it by a conductor, or what I refer to as straight line. And if the source was current, replace by an open circuit. And number 4 is determine the Thevenin's equivalent current. Determines Thevenin's equivalent current. So I Thevenin is supposed to be V Thevenin's over R of L plus R Thevenin's. Then basically this is what we have. Then we go to just examples directly. So the first example, example 1, we're going to have a circuit. We're going to do a circuit here. So this is an example of a circuit that we're going to handle, and this is, if we check to our databases and our reference past papers, we shall be able to see this. It's one of the applications of the Thevenin's voltage. When you look at this diagram, you are being asked to determine using the Thevenin's theorem. We use the Thevenin's theorem to determine the open circuit voltage, part 1, and part 2 of the first section is to determine the equivalent impedance. And part 2 is to draw the Thevenin's equivalent circuit. And from the Thevenin's equivalent circuit, we determine the current flowing. So the first thing we do is to remove the load. The first step is to remove the load and determine the Thevenin's voltage. So when we remove the load, we shall have the circuit appearing this way. So removing the load, this is the solution we're providing. Removing the load. How does the circuit look like? A circuit will look like this. This is 48. The angle is 0 volts. We shall have our capacitor here. We shall have our resistor here and inductor that. So this is minus J32 ohms. This is 52 ohms. And this is J10 ohms. So with the load removed, this is what the circuit is like. So we have removed the load. So we shall be able to determine the open circuit voltage. The open circuit voltage is the load, the voltage in parallel with the load. The voltage across the 52 ohms plus J10 ohms. So after that, then step number 2 is we determine the open circuit voltage. And from that, we shall be able, when you look at this, the circuit is in series. So we shall have our current flowing as current is supposed to be voltage over the total resistance. And our voltage there is 48 angle 0 volts. Our resistance there is 52 ohms plus J10 ohms minus J32 ohms. So this is what determines our current. So basically, I'll advise you this way, that anytime you have got a dividing line, you change everything into polar. Then we can be able to convert it, divide it directly, and then return it back into Cartesian. As it is, this is a mixture of polar and Cartesian. So we shall be having this as 48 angle 0 volts. And we change this, we simplify this, becomes 52 ohms. Minus J22 ohms. This is also equivalent to 48 angle 0. Then we change this into the polar. So we look at the value for the value here for us to convert that into polar, and we should be able to do that. When we convert this, we're going to get 56. This the magnitude becomes 56. The angle here is minus 22.93, minus 22.93 ohms. So that's the magnitude. With this one, we divide the magnitudes and subtract the angles. So if we divide 48 by 56, we get this 0.857. The angle is 0 minus 22, becomes 22.93 ohms. So always present our answer in both forms so that we are able to have the reference point or to get the final the answers very simple, because instead of transferring them, we need them. So, or we can put that in Cartesian. We can put that, this is a polar, then we can put that in Cartesian. When you put that in Cartesian, .805 plus J 0.34 amps. So we have determined the current that's going to flow through that branch. So we need to determine the voltage. So open circuit voltage, VTH, is supposed to be IR. Our I is now 0.857. The angle is 22.93. This is what we multiply by the impedance, 56. The angle is minus 22.93. Not 56, just a minute. Multiply by whatever referred to as 52 plus J10 ohms. So we have to convert this into polar also, so that we are able to get the exact, because this is a polar and cannot multiply by Cartesian. Convert this into polar for us to have a faster way of operating. So if we convert this into polar, that means we're going to put this as 0.857, angle is 22.93, multiply by that. This is going to be 52.95. The angle is 10.885 degrees. So anytime you're multiplying this, we need to multiply. We multiply the magnitudes and we add the angles. So we multiply 0.85, 0.85, 857, multiply by 52.95. This becomes 45.37. At 5.37, the angle is 32. We add we add the angle. The angle is, that's 22.93 plus 10.885. 33.815. This is volts. So that is the open circuit voltage. So we also need to present this value in terms of the Cartesian, so that eventually that we have that. But once you've determined that, that's the voltage. Once we've determined that, then proceed on. We proceed on by determining the Thevenin's internal resistance. So that is the open circuit voltage that we are asked to determine in the first point, the open circuit voltage. So when you look at that, we are already answered the part one. Then equivalent impedance. Thevenin's equivalent impedance. Thevenin's equivalent impedance. We said that when it's a voltage, you replace it by a conductor or a straight line. So that by looking in, when we look in at that point, we shall have our circuit appearing this way. We have replaced this minus J of 32, and this is 52 ohms, and this is J 10 ohms. That's how our circuit will appear like. We have replaced the voltage with its internal resistance, which is a straight line. By looking at this, then we shall have the Thevenin's internal resistance, R Thevenin's. This is product of, we shall have minus J 32 multiplied by 52 plus J 10. Is product of a sum, because the resistors are in parallel. We shall have 52 plus J 10 minus J 32. So we open this, when they open this, what are we going to have? We shall have 32 times 52 multiplied by J. 32 times 52. So we open this, we shall get minus J 1664. J squared is, this become plus, that is plus 32 times 10 to the 20 over 52 plus J 10 minus J 32. When you look back, we shall be able, let us convert that into polar. That means that when we are converting that into polar, then we shall have our conversion being equals to 20. Now this as 1694.489. The angle here is 79.1. Then when look at the below the expression, we had done it somewhere in a previous work. This is 56. The angle is minus 22.93. That's why it's very critical for us to understand where our conversions takes place. So we divide the answers, we get the answer 1694.489 divided by 56. This, we get this as 30. The angle is plus 79.1 plus 22.3 is 101.4 degrees ohms. We convert this into, this is the angle, and this is the internal resistance. Let us convert this into Cartesian. This is minus 5.9293 plus J 29.408. This ohms. Then this is the internal Thevenin's equivalent impedance. which is that the Thevenin's equivalent impedance in the tunnel resistance. So from there, we're supposed to determine the Thevenin's, we draw the Thevenin's equivalent circuit, which forms our part 2. So our part 2 is Thevenin's equivalent circuit. When drawing Thevenin's equivalent circuit, the Thevenin's voltage becomes the source, and the load is connected in series with the Thevenin's internal resistance. So we shall be able to draw the load as it is. Then we shall be able to connect these. This is the R Thevenin's, and the load shall be connected in series with that. We shall have the load as 80 ohms. And this is our Thevenin's, which is supposed to be given as minus 5.9 minus 5.93 plus J 29.408 ohms. So this is supposed to be 45.37. The angle is 33.815. So when you look at that, this is the circuit you are being asked to do. And from here, you are being asked to determine the current. So from the formula, I Thevenin's, we supposed to have V Thevenin's over R of Thevenin's plus R of L as connected in series. And that means that we shall have our 45.37, angle is 33.815 over, we shall have 80 ohms plus, this is minus 5 here, 0.93 plus J 29.408. So this becomes 80 minus 5 point something. 80 minus 5.93. 74.07. So this comes 45.37. The angle is 33.815. This is 74.07 plus J 29.408. Change that into polar so that we divide. So this is 74. So this becomes 45.37. The angle is 33.815 divided by 79. 79.694. The angle is 21.65. When you divide that, we shall be able to get to a final value. So we have 45.37 divided by 79.694. .56. The angle, this is now going to be a final value, which is current. 33 minus 21. This is 12.165 degrees amps. So this is the current. This is the Thevenin's current that the question was asking for, 0.56. The angle is 12.165 amps. the example 2. So, using Thevenin's theorem, determine the power delivered to the load resistor in the circuit shown below. And we shall have our circuit appearing this way. So this is 10 volts, this 2 ohms. And this is 3 ohms, 15 volts, and this is 10 ohms. And this is our load. This is our load. So we remove the load first. If we remove the load, we shall have our voltage, our circuit appearing this way. This is removing the load. We shall have hanging terminals for the load. Then we shall have what I refer to as 3 ohms. Then we shall have 15 volts. This is 2 ohms, and this is 10 volts. So from there, we determine the Thevenin's equivalent voltage, open circuit voltage. VTH, VTH is supposed to be the bigger voltage minus the voltage drop in the bigger resistor. In the bigger resistor. So we shall have, what is the current? I Thevenin's. These voltages are opposing. Then we shall have 15 minus 10 over 2 plus 3. So we shall have this as 10 over 5 over 10 over 5. 15 minus 10 is 5. We shall have that as 5 over 5 volts. It's supposed to be I, current is supposed to be 1 amp. So V Thevenin's is supposed to be, the bigger voltage is 15 volts minus the voltage drop in the bigger resistor. We shall have this as 1 times the bigger resistor is 3 ohms. So we shall have this as 15 times minus 12, 3 is 12 volts. That's Thevenin's voltage. So Thevenin's internal resistance Thevenin's internal resistance, we shall have the 3 and the 2 ohms are in parallel. So this 2 ohms, this 3 ohms. So we shall have that as being equals 2 times 3 over 2 plus 3, which are supposed to be 6 over 5, is supposed to be 1.2 ohms. Then from there, we draw the Thevenin's equivalent circuit. Thevenin's equivalent circuit. Then we shall have that with a load. So this is 1.2 ohms. This RTH. Then we shall have our load was 10 ohms. And my VTH is 12. Open circuit voltage is 12 volts. So I Thevenin is supposed to be VTH Thevenin's over R Thevenin's plus R of L. It's supposed to be 12 over 1.2 plus 10. It's supposed to be 12 over 11.2 ohms. 12 over 11.2 ohms. 11 shall have this as 1.07 amps. Measure. So power supposed to be I squared R, and I is 1.07. We square this times the resistance of the power is supposed to be 10. So that's what we have. Then when we have that as power, we shall have 11.47 watts. So I hope you have been able to follow the two examples you have done today. So we shall be able to continue the two more examples, then you go to another theorem, which shall be also related with this one, which is referred to as the Norton's theorem. So in the next lesson, let us meet so that to proceed on with two examples, to refresh our minds and also proceed with another theorem. So until then, let us meet.